Hello everyone, good afternoon. So we'll initiate the session with breaking into Android IPC mechanism using AIDL fuzzing, right? Just before we begin, a bit about us. So I'm Hardik and I have with me Rajanish, my colleague. We both work at Katem, and recently we have started digging deeper into embedded security, more prominently around Android operating system. And what really motivated us to kind of select this as our topic of research is mainly due to the adoption and popularity of Android platform, which is prominently being used in devices and IoT devices and in mobility as well. And any potential vulnerabilities which are discovered in Android as a platform can impact or potentially have a larger impact to millions of users around the globe, right? In particularly IPC and AIDL are very complex and sophisticated data structures, right? And their implementation is equally as complex as it gets. So we thought this would be a good potential for us to kind of look into it and how it really functions, right? And see if we are able to identify any issues around these implementation, right? Usually when we evaluate any of these devices or platforms, we tend to overlook these components, and these are very underestimated attack surface when doing such evaluations, right? And it has a real world impact wherein it will affect a lot of users who are using it. So we'll quickly go through the objective of today's session. First is we'll look at what is IPC mechanism, how it is implemented, how it is used, how different applications are utilizing this mechanism in terms of interacting with each other. Then we'll dig deeper into the fuzzing framework, how we have implemented it, what is the existing implementation of AIDL fuzzing, and what we have done to kind of enhance its capabilities and providing us with the issues that we kind of get using it. Then we'll also look into the framework which is created and the setup which is there in place. Following that with an interactive demo. And then we'll open the floor for your questions. So now I'll hand over to Rajanish, who would probably dive deeper into the IPC and following points.
Thank you, Hardik, for taking us through a brief introduction of what we're going to present today. So as Hardik mentioned that IPCs and AIDLs in general are a very complex implementations of Android. So when it comes to IPCs and AIDLs, you could see that this is an overview of the entire Android architecture. So there are system maps, there are Java APIs, there are native libraries, Android runtimes, hardware abstraction layer, and in the kernel, there's a small bit which is called IPC. So when you look at that small bit, we cannot undermine the importance that it has in our day-to-day operations or our day-to-day usability of Android. For example, have you guys ever wondered that you open your camera app, which a lot of us are doing right now, you click a photo and everything goes and gets saved to your gallery. How does that happen? Has anybody thought about it? I'm sure now everybody will give a thought on how it happens, and you'll be able to understand the implementations that basically is, responsible for making it happen. So the binder IPC or the IPC mechanism is a very small bit. It's part of the Linux kernel, and this is responsible for inter-process communication. IPC stands for inter-process communication, And it's, as the name suggests, it's very clear that it facilitates communication between two processes. So when we look at an overview, there's a process A, process B. Both of them want to communicate with each other, use IPC, and you're sorted. So there are different IPC mechanisms that Android as an operating system provides. Binders are kernel level IPCs. We have intent, which is application level IPC. And for complex implementations, we have AIDL, which is for complex IPCs. So as security researchers, we have a very intriguing question that why is IPC security important? Why does it matter? So as it says that IPC basically exposes an attack surface of a trusted application to non-trusted entities. So the services are exposed inside an operating system, and anybody residing on the operating system, that could be third-party apps, malicious apps, or even malicious services, can directly invoke those IPCs and cause a lot of havoc. That includes process hijacking, manipulation of data, and even capturing or stealing of data in some cases. Next. So our talk revolves around AIDL. The reason why we chose AIDL is, as Hardik mentioned, that it was a very complex implementation of IPC. And as we proceed forward, we would know that why it is so complicated. And as mentioned earlier, AIDL facilitates communication between two apps. There is a simple structure of an AIDL interface. It's just 2 lines. And when you guys see this, you will say that, okay, there is no logic in place. How does this happen? So we would dive deeper into how an AIDL is implemented by a developer, how the underlying framework is responsible in creating a stub for it, and then how a client and a server interacts with the AIDL. So this is a high-level diagram of 2 processes trying to communicate or talk to each other. So let's say client application has a process which wants to generate random numbers. And the server application has implemented that AIDL that generates random numbers and returns it back to the client. But to do that, there is an underlying framework in place that is implemented by Android, which makes this happen. So to do that, client application cannot just directly go and ask the server application that, provide me with random numbers. There is a process in place which has to be followed. So the client application would create a service which would be rewritten through a proxy that would convert user input into a Marshall data. The Marshall data would be routed through the binder proxy, routed through the underlying kernel, which would have some security mechanisms in place, like UID separations and intent filtering. And then that would go back to the server application and perform the required task. So for example, an onTransact method would be called that would generate the random numbers, send it back to the client, and the client would then display the random number generated by the server. So this is how an interaction in AIDL happens. And as easy as it seems, this gets complicated. So as I told you, that AIDL itself is a very complex implementation, and there is a complex data structure involved that works in the background. As we saw in the last diagram, that there is marshalling and unmarshalling of data that happens. And when the user input is said, it is converted into parcels, marshaled, sent to the binder proxy, and then unmarshaled, processed, and returned back. So when a developer implements AIDL interface, they have to create, just go to your Android Studios, right click on your project and create .aidl file. When you create AIDL file, you declare a method which you want to call. And the underlying framework would create a stub. When you say stub, stub is an implementation which has the methods the underlying marshalling and unmarshalling protocols, and even calling the binder IPCs. So that would implement, Android Studio would implement that underlying stub, and when this is declared, server would implement the logic that would be required to be used by the client. And the client would call onBind service. When the onBind service is called from the client side, the server would wait for the connection from the client through the binder. And when on-service connected call is reached, the binder object is returned, and whatever the implementation is returned back to the client. So when we say client and server, it's not like, something on the cloud and something on your device. Both the services reside on your device, and both communicate internally with each other. One facilitates and other is the receiver. So a simple example of AIDL use case is the audio playback control, which basically, increases the volume or decreases the volume of your speakers. Next. So when we say AIDL in action, it's what I explained in the previous slide, that, okay, it's not very clear, but when you create on the new, go inside your Android project and create a new AIDL interface, you have a very simple looking AIDL file with no logic implemented. And when you compile the app, the underlying framework, next slide, the underlying framework would create a stub which will have basically the complex logic implemented. So as we can see here, the Java, and it has in the parenthesis generated, is something that is a code generated by the framework to facilitate our IPC. So it is the same thing that I mentioned earlier, that the binder client would go through so many underlying layers to interact with the binder driver and then invoke the IPC. So the data flow that happens is bidirectional, and there is a lot of underlying intricacies that caught our eyes, because we've worked with certain clients who have implemented custom services in their application or in the phones, and when we looked at those, we could see that there are certain exposed interfaces which can be interacted by an untrusted application. So that gave rise to our interest in AIDL fuzzing. But before going to the AIDL fuzzing part, what are the security mechanisms in place which are already there implemented by Android? So as you all know, Android is one of the secure operating systems in play. So there are already certain security measures that are already implemented by Android. Few of those is application sandboxing and UID separation. So when we say application sandboxing, two applications cannot communicate with each other without a whitelist in place. And when there is process isolation, there has to be intent filtering in place to allow two processes to communicate with each other. So these are there as precautionary measures, but if the underlying architecture implemented is flawed, this can lead to a lot of vulnerabilities. So the common vulnerabilities that we can see when it comes to Android IPCs is process hijacking, unauthorized access to the system services, and also in some cases privilege escalation. So, and the most common vulnerabilities that we see is data leakage between two apps, that you can send a stub and you can get a response that would give you access to some juicy data. So this is what basically caught our eye, and we started with fuzzing. We started looking for resources on the internet, and because this is a very less explored topic, there was not a lot of information or substance available on the internet. All we could see is a sample pseudocode which was provided by Google's AOSP, that is Android open source project, that told you how you could fuzz AIDL. And the funny part, the interesting part with AIDL fuzzing is it is a grammar-based fuzzing, that you cannot randomly supply anything and expect it to work fine. Because AIDL has its own syntax, AIDL has its own set of variables that it accepts, and if that is not met, it would just reject the parcel and it would wait for the next one. So as the AIDL complex increases, we thought of diving into it, looking at it, and fuzzing it. So this exposed deep-rooted IPC issues and also helped us automate certain process to make sure that the system that is developed is thoroughly secured and handles edge cases really well. So as any fuzzing process works, if any one of you has done binary fuzzing, they would be pretty familiar with how it is done. So we start with identification of the target, then determining of the inputs, of course, then generating the fuzzing data, execution of the fuzz test cases, and then analysis of what happened when the first input was sent to the target of evaluation. And once that is done, we look at the logs that are being generated, and we analyze those logs for any security implications or vulnerabilities. So this is what it looks like from our point of view. So we had an on-device AIDL fuzzer created, which we would be putting it out in the open source so that you guys could try your hands out on any service that is out there. So this is an on-device AIDL fuzzing framework, which is a simple application that generates seed inputs that interacts with your IPC services, underlying IPC service on your device, and starts fuzzing it, saves the logs on the device, and helps you analyze it further. So the tools required is not like state-of-the-art hardware that you need with 100 GPUs and something. It's very simple. You need a mobile phone. You need Android Studios to compile the app for sure. You need ADB to interact with the phone to see the logs that are happening, that are being generated on the phone, and the service you want to fuzz. So we go to the next slide. Because I've been talking a lot of AIDL and service and fuzzing and everything, but how do we interact with those services? Do we have to create applications? Do we have to, do something which would allow us to interact with the service? So if you go back to the slide, Hardik, you could see this is ADB shell interface of any phone that you can have. And there's a utility called service call. So service call is something which allows us to interact with all the services that are there on your phone through the ADB interface. So ADB stands for Android Debug Bridge. So you can just shell into your phone, use this utility to interact directly with the service call. So Hardik would show you an example of how we can interact with the service call. So you'll have to display the phone. So you have a physical Android device, and we have a simple one-line command that says ADB shell service call activity 1. What this does imply, like if anybody is reading this, what do you think that this can happen? 2? So I think demo gods have. So basically we are trying to interact with the underlying service which is there on the Android, and no, so that's not the command. If we just go back to the slide. Yeah. So again, the previous one that you saw didn't work. Is basically UID separation in place, and this allows this showcases the security mechanism already implemented by Android. So we were trying to invoke an activity which this application does not have access to. And that was not part of the demo, but got showcased in the demo. So it's a good example of how secure implementation is there in place that doesn't allow you to interact with the activity service and invoke an activity which is not allowed by the app. So as we can see, we call the status bar, and with certain numbers, we can interact with the status bar to, just pull it up and down. This would look like a gimmick, but this is everything in place that I just told you guys. So this works on the entire implementation of IPC and AIDL, that I'm able to call the service, make the service, pull down the status bar, which is one of the features exposed by the Android for applications to show notifications. And by that, we are able to interact with those services. So now we know that, okay, there's a service call that allows you to interact with the service. Now, what are the services which you can interact with? Just again, ADB inside your phone, and there's another utility called service list, which will list down all the services available on your device. So when you talk about custom devices, Samsung's, OnePlus, or Huawei's, which have some off-the-shelf features. So they'll have some off-the-shelf self-implemented services which could be interesting to look at, and those would be the services which you would like to target. So when you list down the services, you have list of all the services available. Pick whatever service you want, and you can just start fuzzing into it. So as I mentioned, that the only resource available on the internet that tells you what to fuzz or how to fuzz AIDL service is this piece of code published by AOSP, that is Android Open Source Project, which says that, create a binder object that reference to my service, fuzz that service by invoking that object with the first data provided. So this, in 2 lines, gave us a lot of insights that what we could do. So we could invoke the object, we could create a corpus of data, and just start fuzzing that service. So that's exactly what we did, but with a bit more of creativity. So the first service that you see on the right has basically the list of all the valid data that can be processed by an AIDL interface. There's a combination function on the top which generates all permutations and combinations of that available data. And then we have a first service which combines this fuzzing combination and calls the service call, which is the second last line that you can see in the third image, with the code and the arguments which are generated by the combinations function. And that's how the fuzzing starts on the device. So we compile this app, we deploy the app on the device, and I think Hardik would take you forward on how this would happen.
Thank you. So as we saw that we did a walkthrough of what is IPC, what is AIDL, how to have the fuzzing framework up and running. And here is a quick demo of how it really works. So on the left, we have the Android Studio, which actually has the application. And it can be, it is on the user lane. So this is without, it can run without root privileges. And on the right, you have the device. And on the bottom, you have the logcat, which is running. Here we have the application wherein we can just go to select service, list services. So there we have all the services which are currently running on the device. Maybe we can select one of them, NFC or connectivity, for example. Yep. So now we have selected connectivity as a service, and now you see that the fuzzing has really begun on this, wherein it is sending the packets to the service call itself, and hopefully after some time we should see some crash. Meanwhile, if we go through the log file, we already see some panic happening at the kernel level because indirectly you're calling the binder, which is a kernel driver, right? So if you move down, you should start seeing the crashes and panic on the kernel side. And if there is something which the kernel cannot handle, it will initiate a crash on the device itself. So yeah, so one of the sample logs that we have here, which points out at null pointer exception, which was identified. Similarly, there are a lot of memory corruption related issues which are highlighted using this technique. And towards the end, the last 2 lines, if you notice, it's mainly around binder, which clearly states that the kernel becomes unstable at some point in time wherein it is not able to handle the payload which is sent across, and eventually it will crash the device, or it will open doors for potential exploit development. So that way you can actually chain the entire exploit, and then it can impact more users, right? There were when we started looking at this topic, we came across multiple challenges. Firstly, on the complexity of the structure itself, on how it is implemented on the device, and then understanding the structure and understanding how it really works and how we can implement this idea into execution. Also, there were a lot of challenges around the restriction and the sandboxing between the communication of 2 applications, or between the client and server in this case. And then the workaround to that was having specialized characters in play, which in a way bypasses the security which is implemented. And a lot of times when you have AIDLs in play, the structure itself is so complicated. When implementing these services, there are potential chances of you missing out on the configuration part. So there may be a lot of misconfigurations and a lot of input validation related flaws, which kind of help in identifying issues using fuzzing. So yeah, best practices is to, like I mentioned, to have, since it is complex, to have a structured approach, to have least privilege principle, or these days we call it zero trust, right? And we have input validation. So a lot of the test cases that you would have noticed, it is primarily data structures, right? We are playing around with the structures wherein if, say, a boolean is configured, we try to fuzz it with, say, a float value or something else, right? So we are playing around with the data structure in order to receive or come across that imbalance at the kernel level, right? Also strengthening using SE Linux policies, ensuring that only the 2 applications only speak to each other in the set policies, right, which are defined. And plus then you keep on having regular fuzzing activities or regular test cases to ensure that the mechanisms which are in place are good enough, or if there is any need for further enhancements. So yeah, that's us. Now I kind of open the floor for questions if you have any. Good. So I think we did a good job in kind of sharing this information. So yeah, thank you so much.
Thank you, Rajanish and Hardik, for the amazing session. All right, so we were about to we have lunch. High tea. So that's starting from 4:15 and till like 30 minutes. So, yep, we can meet again. Stand up. stretch a bit, stay hydrated.